So this is chapter 6 on uniform circular motion and gravity. Uniform circular motion is the motion of anything that's moving in a circle at a constant speed. I'll try one more time to get a better circle out of that, but I don't know if I can. I can't. And so anything that's moving in a circle at a constant speed, obviously things can speed up or slow down as they're moving, but we won't look at those in this chapter. We're just going to pick constant speed circular motion, and then we'll talk a little bit about gravity. They're kind of related because planets are pretty much doing uniform circular motion. Their orbits are almost circular and they move at almost a constant speed. And there are lots of other things. Cars on clover leaves and stuff are moving roughly at constant speeds in circles. So it shows up a lot. Anything that's spinning, a wheel, will often do that. And so we're going to start out with a little section on measuring angles in radians. I'm pretty sure you've all seen measuring angles in degrees. You know, this would be a 90-degree angle here. All right, that would be 90 degrees. And this would be 180 degrees. And then so on. This would be 360 degrees. It's often convenient to measure angles in radians, and we'll sort of develop a relationship between those. Let me draw another circle here. Right, and so here's my circle, and I'm just going to look at an angle like this one, and I'm going to call it delta theta. And I'm going to say, look, pretend this is a circle. I know it's not a very good one, but pretend it's a circle. This is the arc length, and we'll call it delta S. And that's just the distance. It's just the distance along the circle. And this is the radius of the circle. And so it turns out you can define delta theta, or the measuring angle, the measurement of the angle, as the ratio of the arc length to the radius. And so the arc length is just how far you travel along the circle that the angle subtends, right? And then the radius is just the radius of the circle. And so a simple example is, if we wanted to say 360 degrees, if we wanted to look at that, so the angle all the way around, well, we could say, what is that in radians? Well, 360 degrees in radians is equal to the circumference divided by the radius, right? Because the circumference is the distance all the way around, and that's what the arc length would be, right? And so the circumference of a circle is 2 pi r, and we divide it by the radius is 2 pi radians. And so a couple things to notice. First of all, that means 360 degrees is 2 pi radians. Also notice the r's cancel. It doesn't matter how big my circle is. If I pick any circle and take its circumference, it'll be 2 pi r, and divided by its radius, the r's will cancel. And so the angle in radians around any complete circle is 360 degrees. You can, of course, then look at 180 degrees, right? And that gives me pi radians, because it's half of a circumference. Half of 2 pi r is just pi r, divided by the radius is just pi radians. And if you just go on from that a little bit, you can see that 90 degrees is pi over 2 radians, right? 45 degrees is pi over 4, and so on. 30 degrees is pi over 6. And so if I wanted to calculate, well, what is let's just make up 100 degrees in radians, right? Well, I can just multiply it by 2 pi radians over 360 degrees, because these two things are equal. That'll cancel the degrees, and I get about 1.74 or something like that radians, and so on. I could also say, 1 radian times 360 degrees over 2 pi radians, right? And again, in each of these cases, I'm just doing a unit conversion. We've looked at those already, right? the thing in parentheses is equal to 1, I'm free to multiply by 1 any time. 2 pi radians is the same as 360 degrees. And so 1 radian comes out to about 57 degrees. And so you can do any of the conversions. And so most of the time when we're doing uniform circular motion, and in lots of physics problems, we don't use degrees, we use radians because they're easier to work with. Finally, I want you to note that a radian is the ratio of two lengths. So technically, a radian is dimensionless. Right? Velocity has dimensions of length over time. Radians is length over length. And so it has no dimensions. So you can just drop a radian anytime you want. If you have a radian in the unit, you can just drop it because it doesn't represent the ratio of physical quantities. Or the two physical quantities, it's the ratio of cancel. So angle is position in rotational motion, right? For translational motion, which we were talking about, in chapters 2 and 3, just for linear motion, velocity was change in position over change in time. But for rotating objects, we have the angular velocity, the rate at which things rotate. And that's defined as the rate of change of angle with respect to time. And for that, we use the Greek letter omega, which looks like a curvy W. And we say omega is change in angle over change in time. And so then we can solve some problems. We can say, what is the angular velocity of the Earth about its axis? In other words, the Earth spins on its axis, right, like a top. And so if we want to find out what the angular velocity of it is, well, we know that omega for the Earth, again, I can say on its axis. I realize this is saying a lot, but because we could also talk about its angular velocity around the sun, which maybe we will in a minute. But on its axis is it's the change in angle with respect to time. And if you think about this, if I asked you to do it in rotations per day, could you do that in your head? The Earth rotates about its axis in one rotation per day, right? And that's equal to 2 pi radians per day. If I didn't specify the units, any one of these answers would be fine. I could say the one rotation per day or 2 pi radians per day. I could say 360 degrees per day, something like that. If I wanted to convert this into radians per second, I would have to convert the day and so, there we go. So I would have, so I could cancel the day and cancel the hours and cancel the minutes, and I would get radians per second. And what that comes out to is 7.27 times 10 to the minus fifth. Radians per second. If I wanted to convert it to degrees per second, right, I would multiply it by 360 degrees over 2 pi radians, right, and I would get I would get 4.16 times 10 to the minus 3 degrees per second. So even though the Earth goes all the way around in 24 hours, its angular velocity is pretty small because it takes 24 hours to do 360 degrees. Right. we could also ask the question, what is the angular velocity of the Earth as it orbits the sun? Right. And again, we said, well, it would be omega is equal to 1 orbit per year. Hopefully you know that, right? The Earth goes around the sun 1 time in a year. And what is that? That's just 1 circle. So it's 360 degrees per year. We could write it that way. Or again, we could say it's 2 pi radians per year. And again, if we want to convert this into radians per second, we would multiply it by a year over 365 days times a day over 24 hours times an hour over 60 minutes times a minute over 60 seconds, and I would get 2 times 10 to the minus 7, roughly, radians per second. It's a really tiny number, but it's got a year to go around 360 degrees. And so that's what angular velocity is. And a couple of examples. So we can ask the question now, how is angular velocity related to translational velocity? That's what I mean by velocity in uniform circular motion. So let me just draw this picture again, right? And so here is delta theta, right? And here is delta S. And we say, look, omega is equal to the rate of change of the angle with respect to time. But the velocity, if you're driving your car around this circle, right, is equal to the rate of change of position over delta t. And so it's how far you've gone distance-wise, right? And so we already said that delta theta is equal to delta S divided by R. And so that means delta S is equal to R times delta theta. So if I know the angle, I can multiply it by the radius and get the arc length. And that means the velocity is equal to R times delta theta over delta t, or it's equal to R times delta theta over delta t, which is R times omega. So for objects moving in circular motion, the speed of the object is equal to the radius times its angular velocity, or you can say its angular velocity is equal to how fast it's going on its speedometer, say, divided by the radius of the circle. And so this equation relates the angular velocity to the linear velocity for something moving in a circle in uniform circular motion. So we can ask the question, what is the speed of the Earth as it orbits the sun? We already figured out that its angular velocity is 2 times 10 to the minus 7 radians per second. And now we understand that v is equal to omega times the radius. And so if this is the sun, right, and this is the Earth, well, that should be a circle, but anyway, you get the idea. If this is the radius for the Sun-Earth orbit is r is at about 1.5 times 10 to the 11th meters, right? And so that's, so if we multiply that out, we get v is equal to omega, which is 2 times 10 to the minus 7 radians per second, times the radius, which is 1.5 times 10 to the 11th meters. And that gives us 3 times 10 to the 4th. Remember, we said radians is really not a unit, and so I just end up with, it's dimensionless, I just end up with meters per second, which is what I want for a velocity. And so this is 30,000 meters per second, or 30 kilometers per second, or roughly 18 miles per second. And so that's pretty fast velocity, right? 18 miles a second. So here's another angular velocity example. We can ask the question, what is the angular velocity of a car wheel if the car is traveling at 15 meters per second? And so imagine this is the wheel of the car, right? And so the car's bumper is here or something like that, right? And the car goes up like that. If the car is traveling 15 meters per second, that means the center of the wheel is going at 15 meters per second, right? And so the wheel is spinning at angular velocity omega, and the question is, what is the linear velocity of the edge of the wheel, right? And so what I'm going to ask you to do is imagine the car was stationary and the ground was going by at 15 meters per second. So if you had a camera just looking at the fixed moving with the wheel, what you would see is you would see the wheel spinning like this and the ground going past the other way at 15 meters per second. And that means when the car is traveling at 15 meters per second, the edge of the wheel is traveling at 15 meters per second, because that's how fast the ground would be going by, and the ground is in direct contact with the wheel as the wheel spins. And so that means that the velocity of the wheel, the velocity of the edge of the wheel, is 15 meters per second. So if the wheel's being dragged, it is rolling along the ground and the center of the wheel is moving at 15 meters per second, that means that the wheel is spinning at its edge at 15 meters per second. And since V is equal to omega times R, that means omega, which is what we're after, is V over R, which is 15 meters per second over 0.3 meters, which is 50 radians per second. And so the angular velocity is 50 radians per second.